All right. Hello, everybody. My name is Jonas Müller-Korndorfer, and I'm going to present to you today our efforts towards smart scheduling in OpenMP. This work we developed at the University of Basel, and it's a collaboration between me, Ali Mohammed, Ahmed Elelemi, Quentin Giota, and Professor Florina Ciorba. The work is also sponsored by the Daphne European project, where we are developing a system for integrated data analysis pipelines, and where we are also developing the methods we are going to discuss here today. Now, just a brief outline. I will start by motivating a bit the subject and explaining why do we think or why do we need smart scheduling in OpenMP. Then I will talk about two approaches that we took in the last few years. So one based on expert knowledge and another approach based on reinforcement learning. Then I will show you some results comparing both approaches and finally some takeaway messages. Okay, so why do you think that it's important to achieve efficient scheduling and load balancing in OpenMP? Right? So what we can see in this plot here on the right is the plot is showing in the x-axis the system, the different systems along the years, right? And in the y-axis, the number of cores per node in these systems. And what we can see is that there is a trend of increasingly more parallel nodes, right? So nodes with many, many cores, up to 256 or more cores, depending on the system. So that means we have a high chance for load imbalance, which degrades performance and wastes energy and limits applications scalability. Now, another aspect is if we look at OpenMP, right? What OpenMP construct might be the most relevant, at least at the moment? Now, well, for sure, many of them, and for example, nowadays GPUs are obviously a big part of it, so target should be uh, going up. But we conducted a survey over 111 applications from different sources, from some benchmarks like spec benchmarks and Core 2 benchmarks and so on, and also from scientific applications available on GitHub or something similar. And we look for OpenMP constructs inside the code, right, with an automated script. We looked for parallel for and do loops, task and task loops, SIND operations, sections, and target. And out of all these options, what you can see here in these plots, in the x-axis, again, you see the constructs, and in the y-axis, you see all the applications and their lines of code. I apologize that the font is a bit small, but the highlight is, well, for and do loops is still a really high source of parallelism, right? So people still use them a lot and they are still quite relevant. So in this work, that's what we approach. We approach parallel for and do loops. Okay, now just for clarification, so when you have a parallel for, or here it could be an example in Fortran, in this case it's just C, but when you have a OpenMP parallel for, we can always add the schedule clause, right? And the schedule clause receives two parameters. So the first one, that is kind, that is, we have a few options defined by the OpenMP standard: dynamic, guided, runtime, and auto. And then the second parameter is a chunk. And this chunk behaves in slightly different ways depending on the scheduling technique. So if it's static or dynamic, this is the amount of iterations that will be given in every scheduling round. And if it is any other technique, it behaves as a threshold. So that is, a scheduling technique cannot assign less iterations than this chunk parameter. Now, the options available in the OpenMP, or at least the ones defined by the OpenMP standard, they they are efficient, um, but there might be cases where they don't suffice, or they are not don't offer the most optimal solution, given a combination of application and system, right? And so, in the last 3, 4 years, we have been conducting some efforts to enhance different OpenMP runtime libraries. So, we first approached the GNU OpenMP runtime implementation, where we added a lot of scheduling techniques to it, different ones from the ones defined in the standard. And also, then more recently, we approached the LLVM OpenMP runtime library, and we developed an extension to it called LB4OMP, where we also added many algorithms to this library, right? So LB4OMP contains up to something like 16 or 17 additional algorithms beyond the ones defined by the standard. And well, that created another issue, that is, how do we choose now? How do we select among all these techniques? Which one is going to be the highest performing one, right? And so we are in a certain decision paralysis situation where you have too many options. But the OpenMP standard itself uh, already thought about this issue to some extent by offering the option auto for a schedule kind, right? And auto is um, defined as implementation defined. So the implementations of the OpenMP runtime can decide how the runtime will behave whenever one chooses the auto option. And well, all of this takes us into an instance of the algorithm selection problem. All right. So what are we trying to do? We have a problem and we are trying to extract certain features out of it, and we are trying to reach a certain goal. Now, our problem space is usually an application and a system and how they cope together. Then applications are composed by regular algorithms. Systems might suffer with variability, which might lead to load imbalance. Then the libraries we have offer a portfolio of scheduling algorithms. And finally, these algorithms may try to optimize different metrics, right? So parallel execution time, robustness, or energy consumption, and so on. So the question is then, how do we select? How do we choose the scheduling algorithm? So first, we implemented a few expert-based methods. This work is already published and you can access it for more details. But basically, we extended the auto implementation inside the runtime such that the user can choose among 3 automated selection methods, right? One is basically randomly selecting a scheduling algorithm, and it follows some rules. Then there is an exhaustive selection method that basically try once every technique and chooses the one with the lowest execution time. And there is one method we call expert cell, which follows fuzzy logic to select scheduling algorithms. And these methods, they select among all of these algorithms listed here. And finally, in this work, we also added a something we call as an expert chunk parameter. So this expert chunk parameter was empirically defined based on numerous experiments where we collected a lot of data and we found out that a value in a certain region usually offers high performance. And the image here shows a simplification of the modifications we made to the LB4OMP library, but it also translates into modifications that are required in the LLVM OpenMP runtime library. And so these are basically the scheduling workflow inside LLVM follows a init function that initializes parameters, then a next function which keeps in a loop until all the iterations are consumed, and finally a finish function that cleans everything up, right? So when we implemented Auto, we had to build an infrastructure that in the init function, some parameters are stored and the methods are selected. The next function remains the same because basically it's executing a given scheduling technique. And finally, whenever the finish function is called, the data is stored about how was the performance or the loading balance or something like this related to the loop being executed. Now, our more recent effort is we developed a further extension benefiting from some initial implementation from Auto for OMP, but to implement reinforcement learning methods inside LB for OMP. So we implemented QLearn and SARSA, right? The reward types we defined for the methods are basically loop execution time and loop loading balance. And finally, the portfolio of algorithms that the library can select from is the same as the one for the expert-based methods. And again, the image shows some additional information about the modifications made to the library. And the key point here is this time we implemented the library as an external or pretty much like an interface outside or detached from the LLVM OpenMP runtime. So the methods here can be reused basically anywhere. As long as the right parameters are sent to the functions, the learning will happen and it will return a selection or one method, right? All right, now let's have a look at some results where we compare the expert-based versus the RL-based selection methods. Now, what's our problem space? So we approached 6 applications. Okay, so it's an implementation of the Mandelbrot set, Sphinx, executing the Everard collapse test case. So Sphinx is a code used for astrophysical simulations. And then string using the triad kernel with basically a memory benchmark. Then triangle counting, hack kernels, and Lulesh. Please notice that we highlight the number of loops. This is not the total, or at least not necessarily the total number of loops of each application. This is the number of loops that we modified to use the library. And another important thing here is that all these applications, they are time-stepping applications. So basically the loops are executed multiple times. In our case here, each loop is executed 500 times per execution. And for now, this is a requirement for the selection methods, as we need the time steps to be able to record the performance of previous time steps and to be able to take a decision in which scheduling technique is the one achieving the highest performance in a given combination. Here is Sphinx and these AMD Epic node are highlighted because these are the results we will actually see in more details in the next slides. Now, we are looking for, or we are evaluating loop execution time and loop loading balance, depending on the methods. So this is measured during runtime. And well, when it changes, right? So this is what matters, let's say like this, when it changes from one time step to another. Then our search space is basically the scheduling algorithms portfolio with all these methods. And finally, as I mentioned before, so what we are uh, testing with different scheduling techniques. So for each time step, we are checking the performance variation depending on the method selected. And the main methods that we look at are, well, all of them, but here it's important to highlight Oracle. So Oracle is not a method. It is something we calculate after the execution. So it is a ideal scenario where one, if one could have all the information, right? So we execute all the experiments, then using a Python script or something like this, we check which scheduling technique actually achieved the highest performance for a given application, system, and time step. And then we build the performance of Oracle. So Oracle is the best performance one could think of. And then, of course, all the three expert-based methods, the two RL-based methods, and finally the two modes of chunk parameter. So the default chunk parameter is usually 1 in most OpenMP implementations, including LLVM. And the expert chunk parameter, as I mentioned before, is an empirical value that depends on the total number of iterations or of every loop. So, and you can find more information in the paper. And well, all this combination of experiments, it's a total of 720 configurations, and we've repeated everything 5 times, so a total of 3,600 experiments. Now, here we have a large overview of all the results. All right, I apologize by the font size. Feel free to pause the video and get your magnifier. But we'll move on to more clear results soon. Here we just want to highlight that, well, first of all, in the x-axis you can see all the different selection methods. In the y-axis you see all the application system pairs. And what's important to highlight here is so this is a heat map, and darker shades of red means a larger performance degradation compared to Oracle. So that means how much slower executing an application with one of the selection methods was compared to Oracle, which is this optimal post-mortem calculated performance. Now we have one application that's purely compute bound, several applications like TC, Hack, Lulash, and Sphinx, which are somewhat in the middle. So they have memory operations, but they also do some computation in the loops. And finally, we also approached one application that's purely memory bound. This is to test all the challenge, the possible scenarios that the selection methods may found in different applications. But let us focus on Sphinx, right? Sphinx is an actual scientific application. You so it might show more realistic results. So the first highlight here is that the highest performance, the highest performing expert-based method overall was exhaustive selection. So trying everything once and selecting one technique. this outperformed almost every other method in almost every case, not all cases, but in most cases, including here for Sphinx. So as you can see, using exhaustive selection without the chunk parameter was only 8% slower than Oracle, and using it with the expert chunk parameter um, was actually outperforming Oracle. And this shouldn't really happen, but since Oracle is calculated based on separate executions, this is just in the range of the standard deviation of the executions. So it's just a little measurement difference. Now, for the RL-based methods, QLearn using loop time as a keyword and expert chunk was the highest performing among the RL-based methods. And finally, we can notice that using loading balance as a keyword for the methods doesn't really work very well. We can see that there is a high performance degradation compared to Oracle for all the methods. But let's try to understand this a little bit better. Now, here, what you see in the x-axis is all the scheduling techniques up to the green background, which is Oracle. Then all the expert-based methods with yellow background, and finally the RL-based methods with blue background. And what we want to highlight here is, first of all, some techniques, especially if they are not using expert chunk parameter, they can cause very high overhead compared to Oracle, right? So that is if you only use that technique, not a selection method. And here we can see that, for instance, static is 80% slower than Oracle, dynamic is 600%, and this AWF is 65, and all the others are a little bit below that. Another important highlight is using the expert chunk parameter improves the performance of basically all scheduling techniques, which explains also why when you use a selection method and the expert chunk parameter, the performance is higher. But to understand what actually happened in the execution, we would like to look at what were the methods, or what was the method that achieved the highest performance, and how was the selection of every selection method, right? So what we did is we basically plot for every time step that you see in the x-axis, so every loop instance, every time step of the application, we plot the execution time of the time step and which technique was selected by the selection methods, or in the top left corner, which technique should have been selected, which is the Oracle performance. So here we have some highlights. Well, many of them come together, but basically, first of all, what we can see is, for instance, for random selection, as expected, the selection was not very optimal. For exhaustive selection, we can see that it went through in the beginning all the techniques, and then it selected the one that it should select, the highest performing one. Then the expert method, the method based on fuzzy logic, couldn't really achieve or find the optimal solution. Then if we look at the bottom left corner for QLearn, using loop time as a keyword, we can see that it has a long exploration phase, but at least it finds the correct selection in the end. And finally, we can see that either using loading balance as a keyword or SARSA as the method for selection end up leading to indecision. So here we have some hypotheses. So first of all, Sphinx, the loop that we modified in Sphinx varies along the execution. And that might cause that the rewards given to every technique keep varying. So there is always one technique that's that has a higher reward than the other. So none of them get selected. So they keep varying uh, every time step. And with that, I come to the end of my talk. So first of all these methods are available in the LB4OMP library. Feel free to visit our GitHub and to have a look at the papers that describe the library. So as a general conclusion, for now, it seems reinforcement learning, or at least the methods we chose, Qlearn and Sarsa, are not the most ideal for selection in OpenMP, as they take into consideration the history of execution of the loop, and that's not necessary in OpenMP, as the loops are executed as an instance that starts, executes, and dies, right? And there is no relation between the loop, the initial execution of the loop, and a second or a third execution of the loop. There may be a relation to the logic of the application, but not the loop itself, right? And since they need all this history, they need a very large exploration phase or learning phase, which is very, very costly and not ideal for OpenMP selection. So we see that expert-based methods for now are outperform RL-based selection. And and as I mentioned, we also want to look at one of our ongoing steps is to look into RL-based methods that don't need so much learning to actually start making a decision. And finally, the same portfolio of scheduling algorithms can also be found in the Daphne system, and feel free to visit it if you have data analysis pipelines. This is a new DSL and a system all developed for integrated data analysis pipelines with large scheduling capabilities. Now, something we are working on also is developing selection for scheduling of tasks in OpenMP. We are also developing these automated selection methods for Daphne, as I just mentioned. And finally, we have a almost done work for a library for scheduling in NPI that will also include automated selection methods. Thank you.